Spark ignition engines, also known as petrol or gasoline engines, refer to internal combustion engines that take in a flammable mixture of air and fuel, such as petrol or gasoline, to carry out the combustion process. By nature, petrol is a highly volatile liquid, but its self-ignition temperature is relatively high. For the combustion of this fuel, a spark is necessary to do so. To generate this spark, a spark plug is placed in the cylinder head of the engine. Pulses of high voltages are being provided to the spark plug from either a battery or a magneto, which is an electrical generator. Once the initial spark is generated, the front flame takes care of the rest of the process. Spark ignition engines operate or work on an Otto cycle. An Otto cycle is an idealized thermodynamic gas power cycle that describes the functioning of a typical spark ignition engine. This cycle was introduced by Dr. Nicholas August Otto, a German engineer, and it is the thermodynamic cycle that is commonly found in automobile engines. The Otto cycle is a description of what happens to a mass of gas as it is subjected to different changes in pressure, temperature, volume, addition of heat, and removal of heat. It consists of 4 following strokes, such as the induction or the intake stroke, compression stroke, power stroke, and the exhaust stroke. Each stroke consists of 180 degrees crankshaft revolution, and a 4-stroke Otto cycle is completed through 720 degrees crankshaft rotation. For one complete cycle, there is only 1 power stroke while the crankshaft turns by 2 revolutions. Regarding a spark ignition engine operating on an Otto cycle, let's have this problem. And it states that the approximate and actual spark ignition engine, consider an air standard Otto cycle that has a heat addition of 1,900 kJ per kilogram of air, a compression ratio of 7, and a pressure and temperature at the beginning of the compression process of 100 kilopascals and 10 degrees Celsius. Determine the maximum pressure and temperature of the cycle, the thermal efficiency of the cycle, and the mean effective pressure.
We are given with the following data. Heat added is equivalent to 1,900 kJ per kilogram. The compression ratio V1 to V2 is equals to 7. The initial pressure equivalent to 100 kilopascals, and the initial temperature that is 10 degrees Celsius or 283.15 Kelvin. And we are asked to determine the maximum pressure, the maximum temperature of the cycle, the thermal efficiency of the cycle, and its mean effective pressure.
And for the schematic diagram of the problem, we have the following.
So for the equations to be used in order to solve our problem, we have these first 2 equations that can be found in our Parents Handbook, 8th edition, page 10-44, equation 10-70, and equation 10-71. Also, it can be found in Chapter 3, page 77 of the Introduction to Chemical Engineering Thermodynamics by Smith, Van Ness, and Abbott. Pressure, volume, temperature relations for perfect gases and for adiabatic processes. So for our first equation, we have the final pressure all over the initial pressure is equals to initial volume all over the final volume raised to gamma, wherein gamma is the ratio between the Cp and the Cp value of a particular substance, and in our case, it is air. And for our second equation, we have the final temperature all over the initial temperature is equals to initial volume all over the final volume raised to gamma minus 1. And for our next equation regarding a particular engine undergoing a particular cycle, its thermal efficiency can be calculated by work net all over the heat added is also equals to 1 minus the hot reservoir temperature all over the polar temperature, and is also known as the Carnot's equation. And this equation can be found on page 166, equation 5.8 of the Introduction to Chemical Engineering Thermodynamics book, 7th edition by Smith, Van Ness, and Abbott. For our last equation, for the mean effective pressure that is denoted by P sub F, it is the ratio of the work done during the working stroke of a cycle to the stroke volume or swap volume of the cylinder. It is equivalent to the W all over the difference between the initial and the final volume.
In our problem, we are dealing with air. Air is a diatomic substance, and this gas has a heat capacity at constant volume equivalent to 5/2 R, whereas its heat capacity at constant pressure is 7/2 R. Knowing that the adiabatic factor is the ratio between the heat capacity at constant pressure and heat capacity at constant volume, so as to say Cp over Cv, the value of the adiabatic factor is computed as 1.4. We will use the pressure-volume relationship equation used for adiabatic calculations to compute for the value of P2, and that is P2 over P1 is equals to V1 over V2 raised to gamma. Gamma, being the adiabatic factor, was already computed earlier and has a value of 1.4. The initial pressure is given 100 kilopascals and the compression ratio V1 over V2 equivalent to 7. By substituting the values to the pressure-volume relationship equation, we will obtain that P2 is equals to 1524.5345 kilopascals. On the other hand, by using the temperature-volume relationship equation, again used for adiabatic calculations, we can compute for the value of T2, and that is T2 over T1 is equals to V1 over V2 raised to gamma minus 1. Again, gamma, the adiabatic factor, is equivalent to 1.4, T1 is given 283.15, and the compression ratio is the same. By substituting the values to the temperature-volume relationship equation, we will obtain that T2 is equals to 616.6742 Kelvin. From Table C.1, heat capacities of gases in ideal gas state, found in the Introduction to Chemical Engineering Thermodynamics book, 7th edition by Smith, Van Ness, and Abbott, the ratio between the heat capacity of the air in the ideal gas state and the ideal gas constant is equivalent to 3.509. By multiplying this value by the ideal gas constant and using conversion factors, we will obtain that the heat capacity of the air in the ideal gas state is equivalent to 1.0074 kilojoule per kilogram Kelvin. With the value of the Cp and the ideal gas constant, we can compute for the value of the Cv using the relationship Cv is equals to Cp minus R, and it has a value of 0.7203 kilojoule per kilogram Kelvin. Using the equation T3 is equals to T2 plus the heat added over the Cv of the air in the ideal gas state, given that we all have the values to be substituted in the equation with T2 equivalent to 616.6742 Kelvin, heat added 1900 kilojoule per kilogram, and the Cv of the air 0.7203 kilojoule per kilogram Kelvin. The value of the maximum temperature T3 is equals to 3254.4640 Kelvin. By employing the Gay-Lussac law, P2 over T2 is equals to P3 over T3, the value of P3, the maximum pressure that is asked, can already be obtained, and it is equivalent to 8045.6465 kilopascals. In getting the thermal efficiency of the cycle, we will use the Carnot equation efficiency is equals to 1 minus Th over Tc, where Th is the hotter temp, equivalent to 283.15 Kelvin, and Tc, the colder temp, equivalent to 616.6742 Kelvin, giving us a thermal efficiency of the cycle equivalent to 0.5408 or 54.08%. The last thing to determine is the mean effective pressure. The formula for the mean effective pressure is work done over the stroke volume, or work is equals to V1 minus V2. The first thing to do is to get the work from the Carnot equation. Efficiency is equals to work produced over the heat added. With 0.5408 of efficiency and 1900 kilojoule per kilogram of heat added, the work produced is equals to 1027.52 kilojoule per kilogram. Next is to compute the value of V1. To do so, we will use the ideal gas state equation PV is equals to RT. P1 is equals to 100 kilopascal, T1 is equals to 283.15 Kelvin, and the gas constant 8.314 kilojoule per Kelvin kmol, and convert it to kilojoule kilogram Kelvin by dividing it by 28.960 kilogram, the molecular weight of the air. We will obtain that B1 is equals to 0.8129 cubic meter per kilogram. To compute for V2, use the compression ratio V1 over V2 is equals to 7. With the value of V1, 0.8129, V2 is equivalent to 0.1162 cubic meter per kilogram. With the computed value of V1, V2, and the work produced, the mean effective pressure is equivalent to 1474.6269 kilopascals.